Let's see if someone will be here today after autonomous and mobile robotics. One. Okay, the one that is watching, can you tell me whether the audio quality is good? Because I changed something with the microphone. Single concurrent viewer. Wow. All right, then I don't think you will multiplicate in this time, but I will do the lesson anyway, and then you will watch it with your time. Please try to watch the lesson before the next one, right? So that you will at least know what we will be talking about. All right, so the topic of today is we will encounter two things. One is the 3D point registration, which is a lift of the problem that we have seen last time in 3D. And we will also introduce the robust kernels, which is a way to achieve a more smooth optimization in presence of outliers. Now, let's start with the point registration. Well, the introduction of what is point registration was done last time. I will now just repeat it for completeness. The idea is that we have a given set of points in the word frame, which means that we know these points. We have a device that is able to observe these points in its own reference frame. We have an oracle that tells us which point is which. And given all these premises, we want to find the transformation of the sensor in the word, or the word with respect to the sensor, which is equivalent, because one is the inverse of the other, that basically makes the 2 points to overlap under the transformation. In this context, we will talk about estimating the transform of the word with respect to the sensor instead of the opposite, because the formulas are a little bit easier, but doing it in the other way is completely possible. Now, we have seen how to solve this problem in 2D in the last time, and we also have seen how to apply least squares to approach the bearing-only registration problem, which is, I know a set of points in the word, the location of a set of points in the word, and I sense the angle, the relative angle between me and these points, and based on these relative angles I want to determine the position in the word, my position in the word, or the position of the word with respect to me. We can cast a similar problem in 3D, and we will do it actually, but right now let's focus on a sensor that is able to completely observe these points. So the sensor returns me the XYZ of each individual point. And basically by finding a transform that makes the points in my reference frame to overlap with the points in the word, results in the solution of the problem, or to be as close as possible. Now, let's qualify this problem, and let's use the standard methodology that we have introduced for least squares. First of all, we have to qualify the domain, which is the state of my problem. And in this least square setting, the state contains is an object of SE3. So it's a rotation and a translation in the space. we could represent it in this machinery for now. We will represent it as a 6D Euclidean vector, where the first three components x, y, z denote the translation part, and the remaining three components alpha x, alpha y, and alpha z denote the rotation along the three axes. And you know, or you will recap, that it's always possible to move from this representation to a translation vector and a rotation matrix, this time in 3D. The measurements are, in this case, 3D points, and a 3D points can be expressed as a 3D vector in the space, as an element of R3. So we will qualify our domain Z as belonging to R3. So remember that in this case we said that X belongs to SE3 and it's parameterized this way. In this case we say that Z belongs to R3 and it's parameterized by its own transformation matrix. Its own vector. Sorry, I have a problem with the streaming. Okay. Yeah, Google decided that it wanted to sign me out. Okay, and the measurement is parameterized as a 3D vector. Now, having said so, having qualified the state and the measurements, we can write down our prediction function. The prediction function is a function that maps a point that produces a virtual measurement of a point pi in the world. And given that in our description of the problem, in this case, we decided to use as a state the position of the world with respect to the robot, in order to obtain the position of the point in the reference frame of the robot, I just have to calculate to multiply the point by the transform described by x. And this transform is constituted by a rotation matrix R of alpha, which can be calculated from these three angles, and a translation vector t, which is exactly this one. And this constitutes basically my prediction function. So this is the measurement. So if a point would be here, and the world with respect to the robot would be at R and at t, then I would sense the ith point in this position over here, which can be calculated by this formula. Okay, so now a little bit a recap on the rotation matrices. It's always good to repeat things. We denote a rotation matrix R of alpha as the product of three rotations along the axis. So a rotation matrix R of alpha, where alpha is a triplet alpha x, alpha y, and alpha z, is obtained by using this formulation: Rx of alpha x, Ry of alpha y, and Rz of alpha z, where this is the rotation along the x-axis of alpha x, this is the rotation along the y-axis of alpha y, and this is the rotation along the z-axis of alpha z. Just for your convenience, I added to this slide a lookup of how these matrices are written. So this is a rotation matrix along the x, and you can see that it keeps the x-axis, the points along the x stay where they are, and only the point along the y and the z change. C denotes cosinus of alpha, and S denotes sinus of alpha. Equivalently, the rotation matrix along the y leaves the y component unchanged, because if you rotate along an axis, well, that axis, the things along the coordinates along that axis don't change. And equivalently, this is the rotation along the z. Having the rotation matrices, the three rotation matrices, we can also compute a respective derivative. So the derivative of Rx with respect to alpha x, the derivative of ry with respect to alpha y, and the derivative of rz with respect to alpha z. And this can be obtained by simply saying that the derivative of the cosinus is minus the sinus, the derivative of the sinus is minus the cosinus, is the cosinus. Okay, so this is the picture. So this is the way we describe our rotation matrix. Now, having exploded the rotation matrices serves us to highlight the contributions of the state vector in the prediction function, because the state vector contains alpha x, alpha y, and alpha z, and we already feel that to calculate this derivative we will have to act on these terms. Now, having recapped the rotation matrices, we can go back to the requirements of our ICP. I have defined, recall that I have defined the prediction function. So the error function will be simply the prediction minus the measurement. And given that the measurement is Euclidean in this case, the derivative of the error function with respect to the state is equal to the derivative of the prediction function with respect to the state, because the measurement which will be subtracted here appears as a constant. So let's focus on calculating the derivative, the Jacobian of this prediction function, which we know to be the same as the derivative of the error function for this problem. Well, the first question is how big this derivative should be. How big is this Jacobian? Well, the answer is always this Jacobian is as tall as the error function and as wide as the state, right? Because it's the variable with respect to which we are deriving, and we have one column for each element of x. And then it will have the following structure. It will have a 3 by 3 block here, which is the derivative of h with respect to the three components of t, which is tx, ty, and dz. And then we will have three columns, one which is the derivative of h with respect to the first angle, one is the derivative of h with respect to the second angle, and one is the derivative with respect to the third angle. Now, in order to figure out these three components, I will switch back to the prediction function, and we will see what these formulas mean. Remember, this is our prediction function. And now we are deriving this prediction function with respect to the three components in t. Well, it's quite obvious that the derivative of this object with respect to t is the identity, because t appears here without any multiplicative factor. So the very first block of my Jacobian will be the identity, a 3 by 3 identity. This boy here is a 3 by 3 identity. Now, what will be the derivative of my error function or prediction function with respect to alpha x? Well, then in this case, to answer this question, I have to unwrap the definition of a rotation matrix, the one with Rx, Ry, and Rz. So let's go back again to our prediction function. So I could explode this function here in Rx of alpha x times Ry of alpha y times Rz of alpha z. And everything multiplies p. Now, it's a triplet of matrices that multiplies a point. And each of these matrices is influenced by only one component of the state. The first angle, the second angle, or the third angle, depending on the number of matrices. So, it's quite obvious that given that I know already the derivative of the three rotation matrices because I've written them in the previous slide, it's quite obvious that the t component will not appear because the angles, they do not appear in the t component of the prediction function. And if I restrict myself to the rotation, I will have Rx, Ry, Rz times Pi. Given that I'm deriving, in this case, for this column, only with respect to alpha x, well, and these two elements are constant, I could just substitute in this component the derivative of Rx with respect to alpha x. And then I will put here R prime of x. Then I have Ry, Rz, and P. Equivalently, for the second component, I could derive with respect to, I have to take the formula of the error and derive with respect to the y component, the alpha y component. And the alpha y component will influence this block of the chain of rotations. So I will have to substitute Ry with R prime y in this formula. And equivalently for the z. Observe that these three elements are dimensionally consistent, because this is a vector. Here I have three by 3 matrices that are multiplying each other, which are multiplied by a vector, and the result is a 3D vector. And this is consistent with the location of these 3 vectors in the Jacobian. Okay, so I've written the Jacobian, and then let's assemble, like in a simplistic octave code that we will see in a while, these findings of us. So this function is the classical function error and Jacobian that you will find everywhere from now on, and it's responsible of calculating the error and the Jacobian of given a certain transform x and given a point pi p, which is the point that you know it will project into the measurement, into the corresponding measurement, that should be stored in the z variable. So what we do, assuming that x has the same form of the x vector in the slides, so first the 3 translation and then the 3 angles, well, we will calculate the rotation matrices accordingly. There is a utility file rx that, given an angle, constructs me a matrix along the x, of a rotation along the x of this quantity. Ry is the same along the y-axis, Rz is the same along the z-axis. So Rx, Ry, and Rz small are the 3 rotation matrices along the 3 axes. Then, given that I know that I will also need the rotation the derivative of the rotation matrices, I will also get in 3 variables those derivatives, where Rx prime, Ry prime, and Rz prime are nothing else than the implementations of the definitions that you have seen in the rotation matrix slides. And then, for consistency of notation, we also extract the translational component. Then we construct the prediction. We say that z hat is equal to the rotation times the point plus the translation, which is coherent with the h of x function in the slides. The error will be the difference between the prediction and the measurement. And then we start assembling the Jacobian. We know that the Jacobian has to be a 3 by 6 matrix, because one point is 3-dimensional and my transform has 6 degrees of freedom. So we allocate the Jacobian, we set the first block to the identity, and then we start composing the 3 columns, J13, J1, the derivative with respect to alpha x, to alpha y, and to alpha z, to be exactly consistent with the slides that you have seen 2 minutes ago. Okay, this is the error in Jacobian, and then comes the least square machinery, which is the very same of all time. We will call it do ICP, and we will run the optimization for a certain number of iterations. This function returns a vector of just one. Returns the position that it has found, and returns the statistics of the chi-square during the iterations. So this will be a vector which is big as the number of iterations, and at every iteration we will store there the sum of the squared errors. It's a difference from the implementations in the slides, in the definition of least squares. Here you don't see the information matrix because for simplicity we removed it, but this is equivalent to have an information matrix which is the identity. Like this would be J transpose omega J, this would be J transpose omega E, this would be E transpose omega E. Classical iteration of least squares, we assemble our linear system, and then for each element, for each data point and for each measurement, we accumulate the H matrix and the Jacobian, and we also monitor the error, the residual error of our optimization. And then at the end we apply our we store the current error, which is the sum of all errors encountered. We solve the linear system and we update the current solution with the perturbation that we have computed by solving the linear system. Classical, you have seen it already, I think 4 times, so there's a high chance that it will persist. Now we have everything, we could immediately do the testing. Now, the testing is actually the first part that you have to do when you develop this thing. So you will have to write a simple program that spawns a set of 3D points in the world. You will have to define a location for the robot that you know to be the ground truth. From this location you can compute a set of synthetic measurements of this point just by taking each data point and expressing it in the reference frame of the transform that you have picked up. And then you run ICP. At the beginning, considering that least squares finds might get trapped to a local optima, in order to figure out that everything is consistent, you would start by putting the with an initial guess which is equal to the ground truth, so that you can debug the system and remember that the error in 0 should be 0. If it's not 0, there is some problem in the prediction function. And then you can move it, and then you can see how it converges. And we have already seen that the chi-square, which is the sum of the errors, might go down during the iterations if the problem is well posed. Might also be that you might also choose a configuration, very ambiguous one, where you put the robot on the other side, and then the system might have some trouble in finding the optimum. And then this is the profile of the error evolution. Like before it was starting from here and it was going down very smoothly, but if you start from an odd configuration, it might take longer to converge. And due to the singularities in the angles, you might also have a smooth profile of the optimization. So it might be that at a certain point your chi-square actually increases to go down again. And this is basically ICP in 3D. So with this you can register 2 3D point sets if you know the correspondences. I'm now switching to Octave to show you how to write down this piece of program, or actually just to run it, because the program has been already presented in these slides. Die. These are exactly the same functions that you have seen in the slides. Very, very same. This is the do ICP, so I will not go through it. I will go through the test program. The test program is mimicking the test program in 2D. We have 100 points. We spawn these 100 points into a matrix which is 3 by 100 randomly. We define an initial position for the robot. V2T and T2V. V2T is a function in my library or in the library of probabilistic robotics that takes this 6 vector and converts it into a 3 by 3 transformation matrix. Or this is noise. Okay, yeah, we also could add some noise. Then we compute the measurements, like by simply expressing these points in the reference frame of the robot. And we do this by taking the transformation of the points and expressing it in the reference frame of the robot. That's it. And then we run ICP for a certain number of iterations. Later on, we will add noise and we will see what happens, right? Right now, all the measurements are perfect. We do a couple of tests, one with a good initial guess, which is close to the identity. Then we do a test with a bad initial guess, and we might expect to see 2 plots with 2 different convergences. What we do here in the first round is we call the ICP for this good guess, which is equal to the ground truth multiplied by that we perturbate with a little bit of noise. And this is basically another ground truth that we will see later on that starts the robot at the origin. And so it has to make all the effort to put it where it belongs. Okay? And then good guess, bad guess, we see all these things. And we will have 2 plots out of this program. Do. No. Now it's called the program ICP 3D test. Now it's calculating, and what we see here, this is first the result with the good guess, and this is the result with the good guess that starts from 5, and the bad guess that starts badly. So the take home of this implementation, so to say, is that the initial guess quite matters in order to find the global optimum. And if you have a problem which is really bumping, you might not actually converge to the right solution. In this particular case, the problem is so simple that you find the minimum anyway. Okay, and that's the presentation of this fantastic, spectacular program. Close, close, close. And then we go back to our slides and we introduce another topic of the day, which is the linear relaxation. Now, in this problem, we have seen that we might require several iterations to reach the convergence. That plot was expressing the variation of a chi-square as a function of the iterations. So, in order to go to 0, to go low, you need to do many, many iterations, and that might be quite unhandy. Now, we're asking ourselves, can we do something better? Can we approach the problem doing less iteration or potentially just one round that brings us to the maximum. And to answer this question, we have to think that there is one condition under which the least squares converges in one go. And this situation is when the Jacobian does not change between iterations. This is the fact. Now the question is like, how do we modify the Jacobian? Well, the Jacobian depends on the error function. So in order to modify the Jacobian, we have to modify the error function. And how do we modify the error function in a way that its Jacobian does not depend on the iterations? Well, in this case, if we take the problem as it is, it's not really straightforward, because it's not possible actually, because we are moving on a manifold. We're moving on a space which is not Euclidean, which is the space of the angles. So no, it doesn't work in this case. But we could simplify our life by relaxing some constraints. So if we would relax the constraint that the matrix of the affine transform that describes the position of the word with respect to the robot wouldn't be a rotation matrix, but would be any matrix, then we could rewrite the error function in 12 parameters this time, because I have 9 parameters for this new matrix and 3 parameters for the translation vector. That might be easier to handle. How? Well, we could describe, parameterize our state, which was belonging to SE3, but is not anymore. Now it's in the space of the affine transforms, like a 12-dimensional vector, where the first 3 components are the row vector, the first row of the rotation matrix. The second 3 components is the second row of the rotation matrix. The third component is the third row of the rotation matrix, and the last 3 components, so this is 12, the last 3 components are just the translation vector. So I have a 12 vector in my hands that I need to manipulate. Now, if I write the prediction function, which is equal to the error function minus, with the difference that we don't subtract the error. If we write it as it is defined, as it is actually, and we highlight the role of these vectors in the product of the matrix, notice that this is the first row of the point, so this is this is the second row of the rotation matrix, this is the third row of the rotation matrix, and these 3, they form R, which is multiplied by P and then summed by T. Okay, I have highlighted all the components of my state in this new formulation. Now, this product over here is perfectly equivalent to this other product over here, because the first component of this product would be the dot product between this row and this point. The second component of this product would be the dot product between R2 transposed and P. The third component would be the dot product between R3 and P. Okay, so once I have a dot product can be transposed, right? So I can flip the role of P and T, and I could just rewrite the same equation by saying that the first component is equal to R1 times, so P dot R1, P dot R2 is the second, P dot R3 is the third. This matrix here immediately bloated to be 9 by 9, so 3 by 9, so 3 rows and 9 columns, where these 3 components contain the point, these 3 components again contain the point, and these 3 components again contain the point. Okay, so let's call this new matrix Mi. Surprisingly, if we now calculate the derivative of this function with respect to the components of our state, we figure out that the derivative does not change, because the derivative of this object here with respect to t is the identity, and the derivative of this object here with respect to R1, R2, Rn3 is nothing else than Mi. Okay. Now, and this brings me to the next slide, which is how to calculate the Jacobians. Remember that we expand our state by writing which components are in it, and then we rewrite the error function as highlighting the role of Mi, which is the matrix we have identified before, and we start calculating the derivative. Like the derivative of this function here with respect to the R components will be equal to Mi, and the derivative of this function with respect to t will be equal to the identity. So this is a 3 by 9, this is 3 by 3. If remember that in least squares you always refine a solution, right? But since we are casting a variation of ICP that converges in one iteration, then the starting point is not relevant, and so we could choose as an initial transform just the identity. By setting this transform as the identity, well, results in the following formulation for H and for B, where H is the sum of J transpose omega J, and B is J transpose omega E. So if you take this Jacobian here and you multiply it by itself transposed, and then you sum them up, you figure out that you will obtain the following function for the H matrix and the following function for the B vector. Okay? Cool, right? The problem is that this variant of this relaxation that we have done on the original formulation will find a solution. But the solution found, we never enforced that the solution found was a rotation matrix. So this formulation of least squares will just produce me an R and a T, but R is not guaranteed to be a rotation matrix, and in general it will not be a rotation matrix. A rotation matrix is valid, it would be a rotation matrix only if the three vectors R1, R2 and R3 are orthonormal, which means that multiplied by itself makes 1, multiplied by any of the other two makes 0. Multiplied means dot product. And then once we have this, but another consideration is that if there would be no noise, then the only thing, and if I have enough points, the solution returned by linear relaxation will be a rotation matrix, because it will return me, because that transform could be explained perfectly with a rotation matrix. But in general, in case of noise, we will not have that R represents a rotation matrix. And so, what can we do? Well, once again, we find basically the closest approximation to a rotation matrix of the rotation matrix which is returned by the solution of least squares in one iteration. And one possible way is to calculate the SVD decomposition. The SVD decomposition is one of the many decompositions of a matrix that, given a matrix A, the SVD decomposition is consisting by a triplet U, D, and V transposed with appropriate dimensions. where U is as tall as A and V has as many rows as A, because then needs to be transposed. These matrices here are orthonormal, so both U and both V are orthonormal, and D is a diagonal matrix of the so-called singular values of A. A peculiarity of the singular values is that they denote basically the magnitude of the transformation along the different axes. So if my transform, my matrix A or R, my initial matrix A, which is actually the linear part of returned by the linear relaxation, is a rotation matrix, then D will be equal to the identity, because U is an orthonormal matrix, V is an orthonormal matrix, and in order to stay on orthonormal, this product, then D must be consisting of all ones. Okay. If D doesn't contain all ones, which is always the case, what we do is that we substitute D with the diagonal matrix of ones, or we just like delete D from this reconstruction and we force it to be the identity. Having done that, we can recover. If D would be the identity, well, the rotation matrix will be just the product of two orthonormal matrices, U and V transposed. And then we have enforced our solution to be, once again, orthonormal. So R is again a rotation matrix and we are all happy. Let's see if there are tabs in the chat. Clearly, if the transform return, if I have a lot of noise, I might find any transform. Then by doing the SVD decomposition, I will figure out that what I found is not a good rotation matrix. And in this case, I might, let's say, abort the error. But more than the noise, what is typically painful in this point registration process is that the data associations are not typically correct. They are affected by errors, which we call outliers. And outliers, well, destroy the solution of linear relaxation in general. So, this is what I basically said in the previous slide. So, if you have few correspondences and these correspondences are good, you can go with linear relaxation. What I would like to point out is that this technique can be used in many other circumstances. So you could always describe a problem in its relaxed fashion if you have constraints in the state. Then once you have found a solution for this relaxed approximated problem, then you can later on enforce the constraints that you dropped before by doing some black magic. In this case is the SVD decomposition, but in other circumstances could be a normalization or other techniques that are domain dependent. Typically, after you use linear relaxation to boost ICP, to find an initial guess, and then from that point on, you run in a nonlinear fashion, because then you were sure that the orthonormality constraint will be respected while looking for the optimum. And then now, after this is chat on linear relaxation, it's my duty to show you that an example of linear relaxation in action that you have in the repository as always. Let's try with gedit. Maybe it remembers the font. No. Okay. Now, this is my function that computes the linear relaxation. It's consistent with what you have seen in the slides. X is a set of data points, and P is the measurements, which is wrongly called X here. And I like it so little that I have to call it Z, and P is my data points. Z. Now nothing will work because of that. Probably I forgot something, but the measurements are called Z and the states are called okay. So what we do here is to calculate the sorry. Okay, this is a more compact version of the linear relaxation, which is the classical Hoare formula, but it's completely equivalent. What is interesting, basically, if you wrap the equations that you have seen, you might figure out that this formulation is equivalent to what it's written in the slides, only that here they are using the vectorization function of MATLAB, of Octave. But I invite you to implement it as it is exactly in the slides. Right, for the test, we generate a rotation matrix, which we call R. We generate a translation vector, which we call T. We generate 100 random points, and then we perturbate these random points by 3 different levels of noise. The first noise is N1, which has magnitude 0.1, second 0.5, and the third has magnitude 10. And then we run our fantastic ICP, which goes in one iteration, recall it, under these 3 different amounts of noise. I knew it. What don't you find? X-Num. Okay. So we start from this rotation matrix and this translation vector. Like in case we have 0 noise, then our estimate is perfectly good, right? Because it's the very same. R and T are the very same. If we have low noise, then we start noticing that there might be some little difference in these digits over here. With medium noise, we have more error in general, because like we have more error in the translation and in the rotation, and so with medium noise. We have more error in the translation, actually a lot of error in the translation. So we reported the location of our robot at 0.39, while the ground on the X, while the ground truth was at 0.72. So this basically tells you that if you have wrong correspondences, or if you have a lot of noise, then maybe linear relaxation might hurt you. Okay? Exercise: implement linear relaxation by using the formulas that I've given you in the slides. And this basically And this basically concludes the first stash of slides, the one on ICP. As I said, in this round we have seen, we have always worked with perfect correspondences. So we were assuming that of this pool of correspondences between points, everyone was somehow correct, maybe affected by noise, but every single correspondence was somehow reasonable. Okay. What happens when you have wrong correspondences? That's what we're gonna talk about now. With the second pack of slides. And we will talk about robust estimators, which is a way to deal with outliers, which are wrong correspondences, in many robotics problems. Or in many whenever least squares is involved. Now, let's wrap what Gauss-Newton does. Well, the goal of Gauss-Newton is to minimize a function which is the sum of many little functions, where each of those little functions is typically the what we call the omega norm, which is the squared magnitude of a vector modulated by an information matrix omega, and this vector is the error vector, which is a function of the state x. Okay, so this E is small just to distinguish it. This is a scalar, to distinguish it from a vector, which is the bold version. So this is what Gauss-Newton does. We have a function f, and we want to figure out the x that minimizes the sum of all these contributions. This small ei is defined to be the famous omega norm, right, of a vector, which is defined this way. If omega is the identity, then this degenerates clearly to the squared norm. This is called omega L2 norm in the literature. And in general, we write it this way. No, we put the double bar, and then we put an omega on the bottom and a square on the top. And it's defined in this way. This is a squared omega norm of V, the L2 norm of V in omega. We might also make a small digression and consider that most of the times our omega, our information matrices are not changing during the optimization. We can convert an L2 omega norm to an L2 norm, which means with omega equal to the identity, by using a well-known trick that we have already seen, which is the Cholesky decomposition. We know that omega has to be semi-positive definite, or positive definite in general. So what we can do is to calculate the Cholesky decomposition of omega. This will return L and L transposed, two matrices which are with the same matrix and it's transposed, that multiplied give omega. Now if we expand the expression of the omega norm by putting the Cholesky decomposition of omega in, we get this formula over here. And then we can at this point replace, so to say, the vector v with another vector v prime, which is equal to v, but multiplied by L transposed. And so we might say that the omega norm of v is equal to the norm of v prime, to the L2 norm, the L2 omega norm of v is equal to the omega norm of v prime, where v prime is obtained by multiplying v by the Cholesky decomposition of omega. And this is quite simple. Now we have seen the L2 norm, right? Now let's look at other classes of norm. Another class is the L1 norm, which is the well-known norm of a vector. The L1 norm is trivially obtained by the L2 norm by calculating the square root. And this is what you do when you calculate the Euclidean distance, the Euclidean length of a vector, right? You take the components, you square them, you sum them, and then you calculate the square root. Now, what would happen if in our minimization machinery we would replace the cost function of the cost functions, the E, the errors, instead of being the L2 omega norm to be the L1 norm? This is the question. Well, first we have to see what is the bad thing of having an L2 norm there. Well, the L2 norm grows quadratically with the length of the error, right? So if I have many points which have many data points that have are quite content at the current optimum, or and one point which is quite unhappy, when this one point will push away the optimum by pulling quadratically with this with the magnitude of his error, and in this way it might overweigh the correctness of the solution. So what happens in the measurement is typically the outliers, these wrong data points, have a big error, and therefore, if treated as if they were equal to all others, they would ruin the solution, but they are very few, and they typically disagree with each other. Now, in the next episode, we will see how to deal with a strategy which is called consensus. But now, let's try to embed something in the least square machinery that will make us lessening the importance of these wrong correspondences. And we already imagined that if instead of taking the L2 norm, we would take the L1 norm of these errors, well, a wrong data point will be affecting my solution linearly instead of quadratically, which is maybe what I want. The downside of using a norm which is different from the L2 is that, well, if you remember how we were coming to least squares, is that we started from Gaussian assumption and so on and so forth. If you change the norm, well, you are away from the Gaussian machinery of it. As I said, in general, some associations are not correct, and we need to find out a way how to deal with them. One way is to filter them out. Basically, the idea is that you have a set of data points, you find a solution using a subset of the data points that you have. Based on this solution, you score all others, and then you repeat this process iteratively until you find a maximum number of points that have slow error, which is called a consensus, and this is done in schemes like Ransack. And the other way is the M estimators, which is or robust estimators, which is what we will be seeing in this episode, that have the requirement in order to work of having an initial guess which is good enough, because they decide which point is an outlier and which point is not an outlier based on the actual initial guess. So if the initial guess is poor, they will not work. So normally M estimators are good in tracking context, where you know where your robot was at the previous step and you want to calculate where it is at the next step, because in a small time you can't commit that much error and your estimate is still good. Now, we change the M estimators work, or robust estimators, they work by minimizing the following cost function. So look at it carefully. This is the this object over here is the L1 omega norm of E. So this is basically the square root of the L2 omega norm. This UI, this term over here, there's not a square here. This term over here is the square root of E transpose omega E. And we call this object UI of X. Okay? Now, instead of minimizing just the sum of these objects, we smooth every error by an object that we call a robustifier, which is a function that has to be monotonically increasing of the L1 norm. So we minimize the sum of rho of the L1 omega norm of all the contributions. So UI is the L1 norm, and rho is a generic function that has a requirement that it has to grow with the magnitude of this object over here, because otherwise we wouldn't be minimizing the correct thing. So the larger the error, the larger the rho of the error should be. Clearly, if I would choose a rho which is equal to rho of u, which is equal to u square, well, what I would be doing is just to put a square here, and I will end up to the plain standard Gauss-Newton algorithm. Now the game is there's a family of rho functions that have different behaviors, and I will just show you a slide that mentions some of the possible estimators that are around. Here, this is a slide copied by a paper. Thanks, Silver and Concha. And this is the shape of the classical rho function that we see. So if we choose 1/2 r square, r is u, then we have the classical L2 norm. If we choose just the norm of r, then we have the L1 norm, and then there are others, okay, which have this shape. Observe that if this is the error in 0, or the value of u in 0, all of them are increasing as the error goes away, as the L1 norm increases. So on the x-axis you have the L1 norm, on the y-axis you have the rho function. Okay? And there are different methods and different behaviors. You might imagine, for instance, that a function like that, right, or a function like that, might have, this is the truncated, might have the effect that your optimization will have a Bayesian of attraction around the data points that are correct, but if the error is too big, then these points will be weighted constantly, so they will basically disappear from, or not be counted that much in the optimization. There are also functions that, okay, this is the behavior of this, and equivalently also others. This is strongly attracting when we are close, and then smoothing down when we are out. So already you can imagine the behavior of a robust cost function, that if you have a set of data points which are close where they are and one which is off, these ones that are close are kind of snapping, they are pulling strongly, while the one that is far, well, it will be disregarded with respect to the others. It's a way of modulating the L1 norm. Now, this is the general machinery, and then we would like to modify, because we are so in love with our Gauss-Newton, we would like to modify the Gauss-Newton algorithm in a way that we can embed this L2 norm into the machinery, this rho function into the machinery. So let's remember always that to minimize a function, we always need to set its derivative to 0, right? Now, let's see, for a rule of completeness, what is the derivative of the L2 norm of a function. Remember that of the error. The L2 norm is e transpose omega e, right? And so if I compute the derivative of this function over here, it will come out to be 2 e transpose of x times omega times the derivative of the function itself. Okay, this is the classical application of the chain rule. No, the derivative of f squared is 2f times f prime. This is 2f, there's an omega in between, times f prime. Okay, this is the derivative of the L2 norm. Remember it. Now, what is the derivative of the L1 norm? Well, the L1 norm is nothing else than the square root of the L2 norm, as I've written here. Well, then what is the derivative of this function? Well, there is the derivative of the square root, which is 1 divided by 2 times the square root of the argument, the square root of the argument, and so the argument is the L2 norm, so we could just like remove the square root and the square here and leave here the L1 norm, times the derivative of the argument, but the argument is just the L2 norm, and so we can just copy and paste later on the derivative that we have computed in the previous slide. Now, let's call the L1 norm for, and then the 2 and the 2 gets deleted. Now let's call the L1 norm evaluated in x with a scalar function of x, which we call u of x. Okay, and then by doing so, we could simplify this formula here into this more compact form. And we notice that this the L1 norm is the product of a scalar, which is the inverse of the L1 norm, and the derivative of the L2 norm. Okay? Having done that, we can calculate the derivative of the error function of rho of the L1 norm after passing through the robustifier, this robust cost function rho. So how do we compute this derivative over here? Well, we use the chain rule as always. So the derivative of this object, which will be the derivative of rho evaluated in u, where u is equal to u of x, multiplied by the derivative of u of x. But we said that u of x is the L1 norm, which has a derivative which is, we computed before, is 1 over u of x multiplied by the derivative of the L2 norm. Like this object over here is equal to this object over here. And this object is the derivative of the L1 norm. Okay? Hope it is clear. To the 5 that are listening, do you have questions? Is it clear so far? Well, I wait for the latency. Yes, excellent, Mariam. All right, so this is what I have. Then I can keep on manipulating this object, as we always do, and I can expand. This is the derivative of the L2 norm. I've computed it before. I copied it here, and then I have this other object over here. And then the final step that I will be doing is to define a function gamma of x, which incorporates all the ugly things, so this part over here, that in the end multiply the L2, the derivative of the L2 norm. Okay, so all this rubbish over here becomes a certain gamma of x that I know needs to be a scalar. Okay? Okay. Now, at this point, we have a fantastic function that we call gamma of x that is massaging our L2 norm in order to make it equal to the derivative of our robustified cost function. Now we can put the side by side, one on top of the other, the derivative of the robustified function and the derivative of the L2 norm. So this is the derivative of the robustified function, where we use the gamma of x to encapsulate some terms, and on the bottom we have the derivative of the L2 norm. They look similar, right? Or well, gamma makes a big game. Gamma is a number in our system. It's number it's a function of x. But in an iterative machinery, we might think about calculating gamma at the previous iteration and using it at the next, basically. And so we could this gamma over here, this part of the equation is the same, right? There is only a tiny little scalar that makes this formula and this formula different, which is gamma of x. But then we can come out to a variant of least squares, which is the so-called iterative Reweighed least squares, that at every iteration recalculates this gamma in order to conduct the optimization. And this gamma over here is a term that can be easily absorbed into omega, because if you take omega at one iteration and you multiply it by gamma, then basically the two derivatives are the same, or have the same form. This will be just omega prime, a new omega. Okay? And then, with this machinery, we figure out that we could just apply this trick into our optimization scheme in order to get rid of the outliers. How do we do that? Well, that's a variant of Gauss-Newton with the robust cost functions. It's exactly the same as the standard Gauss-Newton. It starts, as always, by clearing H and B. And then at each iteration and for each measurement, you have to compute the error, you have to compute the Jacobian, as you were always doing. And then, well, we have to calculate this famous gamma function. But the gamma function depends on the L1 norm, which is the square root of which is the square root of I don't like it. Of the EI to the square. And then, after doing that, you update gamma, you update the quadratic form with the new gamma, which is put in between the previous information matrix and the current, between the previous the standard information matrix. So this term here is a number that is scaling down or up the information matrix in order to modulate the error. Then you solve the linear system and you apply the increments. So this block over here is the machinery that is induced by the robust cost function. Okay? No, U is the square root of the norm of E, of E square. It should be just in bars. This should be just bar, 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 bar. Well, we're done. This is all what you need to do to implement a robustified cost function. And as an exercise, I will leave you the task of applying a robustifier to ICP. And next time I will show you. Choose any robustifier from the table before. And considering that I have only 9 concurrent viewers, and many are kind of wasted, I don't want to go too much on. I will now kick in a Zoom meeting in case you have questions on anything. And Tiziano, if you're listening, can you trigger a Zoom and send the link around so that I will switch system? So see you in 5 minutes on Zoom if you have questions, and this recording ends here. Thanks, Tiziano.